We now have the last talk for today. We'll talk about another application in the identity space, authentication. And here's Peeter to tell you about authentication in browsers.
Yeah, so hello, indeed. So this is another application that we did. And let me tell you something about it. So this was actually done in the chess project, so it's kind of fitting for this event. Yeah, we gave the same talk, actually, or more kind of the same talk 10 days ago in another ZK related event. Yeah, with my colleagues. So what is it about? So it was about. I mean, we did this together with our partners. Time and also Masaryk University. So if it's time, then it's about blockchain. And I mean, you think that the user wants to post a transaction to the blockchain, which of course he has to sign, but he doesn't want to manage his own private keys. So let's somehow delegate the problem, or well, just move the problem somewhere else. So that instead of the user managing his private keys for the blockchain, he has a relationship with some OAuth providers, and he can authenticate himself to this provider, get back these JSON web tokens. This JSON web token can contain various things. It could, for example, contain the same transaction that he wanted to post. There is a new problem that, besides this transaction, this JWT may also contain many other things that the user maybe does not want to post to the blockchain. And of course, you have been here for the whole day, you already know what to do. That you do not post this JWT, which is signed into the blockchain, but you post the zero noise proof that you have this JWT. There was a paper like 2 years ago that proposed exactly this thing. Okay, and then let me talk what it proposed and what we didn't like there and what we then try to do. So basically, let's say you have a user, he has his browser, he somehow accesses whatever page he accesses in order to create the transaction that he will post to the blockchain. So we specify some transaction. We do one more redirection. We create an ephemeral signing key and verification key. So this is ephemeral thing. So this transaction is going to be signed with this SKU, but then this VKU will somehow be included in this JWT. So somehow from this JWT, so we request this, contact this OAuth provider, request the JWT, some sort of authentication happens here, and JWT will be returned. One more step which I do not really want to discuss, which is about making the transactions by a particular user not so easily findable in this distributed ledger. So let's say basically get some other random number which is somehow deterministic but also unpredictable. So look at the ZK login paper. So we did implement this part, but say and what is this? How does this look? This is visible. You can see there is some light gray bubbles. Anyway, so there is. So what is the ZKP about? Of course, the ZKP is about. I'm having this JWT which contains this verification key VKU. So this is ZKX is the instance known both by the user, or the browser, and also by the blockchain, and ZKW is the witness, and the witness includes this JWT token. It includes some more random numbers, and the instance includes also the users. So it includes the name of the issuer, the public key of the issuer, and things like this. And you will prove that something like this it's very token verifies, this is initial verification, and you prove that the VKU is included here. under some hash, and ZK added is also constructed somehow from the username, the issuer name and stuff. And you have this short zero knowledge proof, and now you push just everything to the blockchain, so the transaction, the ephemeral verification key, some timestamp T, the signature of the transaction, and also the zero knowledge proof. And this, in the ZK, these people who wrote the ZK in paper, they use Groth16 snarks to create this zero knowledge proof, which produces very short proofs, which are good for verification, but these are expensive to generate. So actually, we have this relation is actually quite complicated here, and this Groth16 is quite expensive to generate. So they cannot do it in the browser. So they actually propose to outsource the generation of the proof, which is not so nice. Basically what we had, can we do something somehow better? So instead of expensive proof generation, but then short proof and simple proof verification, let's seek some other trade-off. Make proof generation cheaper. Maybe the proof becomes longer. Maybe it's no longer succinct. But can the proof be generated in a browser? So and with chess, we have the possibility to study this problem. And what technique would we use? NPC in the head is one that is where the proofs can be quite cheap to generate. All of the proofs are going to get long. Let me tell you how this works. I think this is a quite neat protocol. So So basically, what it means. So we have here our prover, we have here our verifier here, and then they both there is this relation, so that they both have this instance X, and the prover wants to convince the verifier that he knows some witness W, such that the relation applied to the X and W gives you 1. And they will do it so that prover, by his own, does some secret sharing of W, and by his own, he thinks that there are several little parties inside his head. And now he gives to each party in his head, he gives the instance, and also to each party in his head, he gives one of the shares of the witness. So it's like each small party in the head does not know the witness. And now he, again, inside his head, so just playing all the parties, he runs a protocol. So playing all the parties of the protocol, and the protocol is such that, it takes the instance from each party, and it takes the secret shares of the witness, and it computes the relation. So the output of pi r, everybody gets 0, 1. The protocol must, as I said, it must compute the value r. Also, it must be a secure multi-party computation protocol in the sense it must be secure against an adversary that can learn what up to 2 of these little parties know. And once the protocol gets gets inside his head the view of each little party, all the messages that each little party gets and all the computations that each little party does, and sends, commits to each view, which means basically, you think, computes the hash of each view, sends them all to the verifier. Now, verifier asks for the views of 2 parties, 2 little parties to be opened, and he sends this over, and now verifier checks whether they got this, that relation accepts, and also that the views are consistent by themselves and also with each other. By themselves means that, the computations that they do, they are correct, and with each other means basically that whatever one party sent to another is what the other party received from the first one. And this, of course, it is possible for the prover to cheat, but the cheating what the probability of being caught when he cheats is at least 1 over n squared, where n is the number of parties. So if you just run this protocol several times, then the probability of cheating goes down. It is also zero knowledge because, because the protocol by R is secure against 2 passive corruptions, which means that these 2 views do not reveal anything about W. Which is, it can be made non-interactive using Fiat Shamir. And why it's nice, internally it used this protocol by R, which only had to be secure against passive corruptions. And well, passively secure multi-party computation is rather flexible. You can do a lot of different things there. And we need this lot of different things in this ZK login relation. Like we need to work on large feeds, we need to work with bits, we need to work with small values, we need to do various kinds of operations. Passively secure MPC can match this. And so when we started this out in the chess project, we thought that we do some quick experimentation and then we are done. That was 2 years ago. And we were looking, okay, so we are not going to write our own MPC in the head implementations. We are taking something existing. We looked into the GitHub. We actually found very little there, which was kind of surprising. We found this protocol called ZKP++. It's a very simple protocol, rather elegant, I would say. The code was easily understandable. Of course, the whole code, okay, it was just 6,000 lines of code, I think. Even then, half of it was just computations with large integers. There's another protocol which is called this Kolesnikov 1, which I actually would have liked to use very much, but one implementation that we found, had no documentation and it didn't run. There are other things, but I think these other MPC in the head implementations, now these protocols are somewhat less flexible. We need all the flexibility. So anyway, we took this ZKP++ and decided that whatever new we need, we will add to it. Of course, we are Cybernetica. We have ZK secrecy. I think Martin told you about ZK secrecy. It is a domain-specific language for these statements that you may want to prove in zero knowledge. And again, pretty flexible one. We have a variety of data types which we intend to use. But yeah, so we had here the comparison between DSLs versus virtual machines, ZKVMs. I think here in Cybernetica we are very much in this DSL camp. So we are more flexible. Okay, basically it's DSL is a more surgical tool than a VM. We have done these domain-specific languages for privacy-preserving computations now, close to 20 years. We have this ZK secrecy compiler. It is integrated actually with a bunch of different backends. Probably maybe the names to tell you. Different zero-knowledge proof implementations and also different circuit representations. And also you can also take some different formats of inputs in. But okay, so this so we already know how to integrate with various backends. So we expected this integration with ZKP++ to also work nicely. There are, as I said, so we need many different data types. The ZKP++ already implemented some of these rings over which you may want to perform computations. We added a lot more there, and also importantly, we added the support. We added the possibility to use several rings at the same time and to convert between different rings. So again, you need to go from bit strings to these elliptic points and a lot of different conversions that you may want to do. All these conversions somehow go through these bitwise shared rings. These ones, Z2 to the power of k. These like bitwise rings. So where the addition is XOR bitwise okay, multiplication is AND bitwise. Yeah, it was kind of important to make these implementations well fast because I wanted the proof to be generated fast. I mean, this is going to be run by the prover who is going to run in the browser. Okay, we also had changed the type system of ZK secrecy so that we could support all these new kinds of things. Actually, before we started working with ZKP++, ZK secrecy, all the data types were fields. I mean, the pure data types were fields, but now we have more, like the type system was extended. Yeah, okay, this is just information. Okay, so we have ZKP++ is a ZK proof backend. We need to encode the relation. Okay, I guess the authors of ZK login, they did encode the relation, but I mean, we had to encode it again. There were some straightforward things to be encoded, like, well, just equality checks here. But there are also some more interesting computations. There is, I mean, JWT has to be parsed. It is because you have to take the values of fields out of it. We simplify the task a bit, and they simplify the task of it. We already assume that this JWT is correctly formatted. I mean, it is I mean, there are these fields are correctly limited, etc., etc. Makes things easier. Basically, then the parsing actually reduces to finding a slice of an array. Okay, array is basically then an array of characters that contains your JWT. You must take a slice of it from a position that is okay. JWT itself is private, and the slice is also the location of the slice is also private. The length of the slice is public, of course. Yeah, you have the base 64 encoding. You have the computations of hashes. I mean, this JW2 verify, it contains hashing here. And there are more hashings here. You could use, I mean, here you use SHA-256 because that's standard. Here you could, I mean, in these hashes, I mean, you could actually choose any hash function that you would like. For example, Poseidon. We experimented with Poseidon. Turned out that SHA-256 was faster. Yeah, we need to do the signature verification of the ECDSA. Okay, and let me quickly go through. So what we did with these interesting parts, well, we contributed with these interesting parts. So that, in array slicing, we made it faster. I mean, the ZK login paper had a rather straightforward, naive implementation of slicing, but we found a way where recursively reducing the size of the JWT, basically. And so this asymptotically decreases the amount of computation you have to do in the relation, and also practically decreases it. For base 64, it was what we contributed was finding some nice formulas that convert from basically 6-bit values to 8-bit values, and following exactly the specification in RFC, whatever specifies base 64. Another important that makes things faster is executing several conversions in parallel. So this again, so these things are now important that we have them. This bitwise sharing is important there. SHA-256 also bitwise parallel execution is an important part. We had some. I mean, ZK secrecy contains some control flow constructions which help to encode this. ECDSA verification now, after we have all these things implemented and all these conversions implemented between the different things, I mean, there wasn't actually much more left to do. Okay, we added some more things into ZKB++, which is okay. I mean, this implementation that you found in the GitHub was very much targeted towards constructing signatures from identification protocols. Like, I mean, Schnorr signature is made from Schnorr identification protocol. So they only had implemented as much as they needed for this. Well, we added all these other constructs there. And yeah, then we integrated it. So, okay, again, technically, just how we did it. ZKB++ was implemented in C++, and it expected this description of the circuit as a implementation of a class with certain methods. So we just, from ZK secrecy compiler, we generate C++. Okay, and then we will compile the C++ into whatever we needed to execute it. When you look at the local benchmarks that we did, I think about was done maybe in October last year. The whole thing, I mean, like I said, the main thing, 50 megabytes for the proof size, which of course is quite a lot, but Anders Ojamaa managed to integrate them into this alpha bill, which was card times blockchain. And also, but the running times were now pretty, I mean, what we need to do was, I mean, the prover basically first has to run this thing, and then has to run this thing. And they verify first parts of this thing, and then this thing. So the prover time is the most important. So this here, like you see, 2.5 seconds. Which is like, but this was like a, let's say, this local execution in the sense that it was compiled into a binary and then done. Here is, okay, once more, okay, I already told you about the ZK login flow. This basically is again the same ZK login flow where we, okay, actually all the things that we do only affect quite a small part of the, I mean, it's the ZK proof generation here and ZK proof verification here. And yeah, when you, we did integrate it into browser and into the alpha bill mostly. I mean, what we have here is, yeah, we have this relation that I now described to you together with some additional implementation, because I mean, this, some of this signature verification was not fully integrated into ZK secrecy, so you just had to have like call another function written in Rust. From ZK secrecy compiler, you get this circuit container.cpp. You get another Rust program which okay, it does the witness expansion, so it turns the witness into a format that this actual proof uses. So, for example, if you want to okay, let me then maybe not try to come up with examples right now. Anyway, so you have a Rust program here, you have this circuit container that we produced, you have the rest of ZKBPP also with a lot of additions from us. Actually, now after this project, this ZKBPP.cpp is twice the size it was before. So yeah, you can, we have like compiled them all into the prover module, which is in WebAssembly and actually runs in the browser. We also can configure this thing as a verifier, and this would be then integrated into this blockchain validator program. So that so that this can be, once the transaction together with a pretty large proof has been posted into blockchain, then the validator will check that it's indeed correct. I think here we didn't, in the end, manage to integrate everything, but I mean, we have, again, running it locally, but I think we didn't integrate this expand witness in the end, because we just, well, we're running out of time and money. But then, yeah, this is actually my last slide, so this is maybe the most interesting. So did we, in the end, achieve acceptable running times inside the browser? I would say that yes, we did. So you see, the approver has to do, both steps, and it's less than 5 seconds. Okay, this is of course, if you think of the user experience, the user will, he has to wait for, he has to go through all these steps here. Okay, so this part takes 5 seconds, the other parts, okay, this doesn't take anything. This asking for the salt takes some time because it's interactive again. But still, the running times are acceptable. Yeah.
There's a minute or 3 for questions, if there are any. Yes. Microphone is coming for provenance and videos. It's on your left.
Eugene, I just want to clarify. So, man-in-the-middle attack. So, could you comment on that? And is a browser the worst kind of software you can use? In principle. So how?
Yes, you have quite a deep software stack, I guess. So.
Man-in-the-middle attack. You need extra effort to provide.
Okay, I guess there are probably a lot of places where you put this man in the middle. Let me. So, okay, this is the ZK login flow. So, well. It's not so much. Of course, this posting the transaction into the web. Here everything is like signed and has approved, so you don't really. The man in the middle, he can only break things, he cannot create things. Of course, well, what happens now in the browser? Yeah, maybe if you have compromised the browser or compromised the OS under it, then at least you probably can leak something to somebody else. Okay. But that's the software stack. This stack here, yeah, should think of it as trusted.
Okay, thank you.
Thank you. Is there one more question? Yes.
So what would happen if you could design this JWT token or OAuth protocol by yourself, so it's specifically good for ZK proving? Because I see that the main bottleneck is that overcoming the legacy protocol.
Yes, this, okay, again, would use some, this kind of signatures with efficient protocols, Kamenish-Lysyanskaya signatures, for example. Choose some of these kinds of signatures and also like some sort of formats where I don't have to parse, but the fields are some already given.
So will it be 100 times faster?
I have no idea, but sounds likely. Faster and also smaller. Maybe not, of course, Cloth 16, it's, specifically consists of only 3 group elements, but, even if it's kind of the same size as the JWT itself, still would be okay. No?
Okay, thank you.
Thank you very much, Peter.
Thank you.